Entropy, okay, this really deals a lot with the second and third law of thermodynamics. Entropy does. What? Okay. Entropy deals with the second and third law of thermodynamics. Entropy is a measure of well, I'm not even clicking the right thing. I'm on the right screen. Entropy is a measure of the disorder of a system, okay? It's the measure of disorder. The higher the disorder, the higher the entropy, okay? Solids are very ordered, aren't they? So they have very low disorder, so they have very low entropy. I know I didn't. I was thinking about that last night. I was thinking. Entropy, solids have, now this is a key thing, solids have very little entropy because they're very ordered. That table is ordered. The particles, while they are moving, they are so tight together, there is very little room for them to move. Liquids can move more than a solid, can't they? So they have more entropy. They have more entropy than a solid does. And then a gases, you know, the kinetic molecular theories in there, they're moving in random straight line motion. So gases have the highest entropy, okay? So there's a couple things we're going to do with entropy. We're going to calculate entropy. I'm not going to spend any time. Sorry, back to it. Third law of thermodynamics. At 0 Kelvin, entropy is 0 of a perfect crystal, okay? Entropy typically, entropy is positive. The standard entropy values are found in Appendix K, which is what you have, okay? So found in Appendix K, which you have. So you can either mathematically, elements do not have an entropy value of 0, only an enthalpy value of 0, okay? Only thing that has entropy value of 0 is a perfect crystal at 0 Kelvin. I don't know. Something that's purely a solid, okay? Not something that is, can be a solid, you know, it has to, different things have a different pure crystalline structure, okay? Like diamond is a crystal, graphite's a crystal, okay? But which one is more of a perfect crystalline structure would be the diamond. Hope I answered that the best I could answer.
Do you happen to have a
no, ma'am, not anymore. I do not. So you can calculate the standard enthalpy change. Now, here's the big thing in this. This is in joules. This will make a big difference on Monday. Standard entropy is in joules, not kilojoules. Enthalpy is in kilojoules, okay? I could work this out. I'm not going to. Guess what? It's the exact same thing you did yesterday, except for one difference. What's the difference between today and yesterday calculated like this? Well, two differences. It's in joules, and you use S, delta S, not delta H from your appendix, okay? Exact same thing, exact same thing, I think. Now, here's what the other focus of today is going to be is we can calculate, okay, so let me back this up. If your entropy, if your delta S is positive, you are increasing entropy, okay? You are increasing entropy, okay? You're getting more disorder. If it's negative, you're decreasing entropy, okay? So that's the question about this. When they ask for the sign, you either put positive or negative, okay? Or increasing or decreasing. When they ask these questions, you can do that. The other thing you can do is to predict entropy change without calculations, okay? It's going to be using what we know. We know that phase changes. We know that solids have less entropy than a gas, correct? So if you go from a solid to a gas, you're going to increase entropy. So melting, boiling, and sublimation all increase entropy. Melting's going from a solid to a liquid, you're increasing entropy. Okay? Boiling, liquid to a gas. So if you're going further closer to the gas, you're getting more energy. You're increasing entropy. Other things, if you go from a liquid to a solid, solids are more ordered, so you're decreasing entropy. Temperature changes. Now, how is a temperature change going to affect entropy? Based on what you know about temperature. When you increase the temperature, what happens with the particles? They speed up. So if things are speeding up, are they becoming more or less ordered? They are speeding up, they're becoming less ordered, so entropy would increase, okay? Entropy would increase. If you increase temperature, you increase entropy. And we kind of know this by what has an entropy value of 0? something, a perfect crystal at 0 Kelvin,
Yeah.
that's the coldest we can get, isn't it?
And when it's at 0 Kelvin, there's no movement at solar order.
Yes. So decreasing, so that's one. Volume changes. Now here's where they kind of get a little difficult, okay? Now let's think about entropy in terms of volume, okay? Is it more ordered? Is it more ordered to be in a big or a small area? What would be more ordered? I mean, more ordered. Yes, more ordered would be a small area, okay? So the bigger the volume, the more disorder, okay? The more disorder. I think of like in here, okay? I can put, it's kind of a hard way to think about it. In here, I could put you right now in somewhat order, can't I? In the whole school, are you as ordered? There's a lot more places for you to go, isn't there? In a bigger school. So that's how I like to think of volume. In here, there's not a lot of places for you to go, like what thinking like playing hide and go seek. Okay? And here there's only so many places you hide. You get a bigger area, you have more places to hide, so you can be more disordered. So increasing volume increases entropy, decreasing volume decreases entropy. Now, what about pressure? What do you know about pressure and volume?
I got that question wrong on this. I don't know.
They are inversely proportional. So pressure would be the opposite thing, wouldn't it? So an increase in pressure would decrease entropy. Okay? An increase in pressure would decrease entropy. Does that make sense? Because if pressure goes up, volume goes down. If volume goes down, pressure goes up. If you would decrease pressure, you would increase entropy. Okay? Entropy and volume are backwards. If there's no reaction, if you mix things together, there's more disorder. I mean, I think like, where's Waldo? It's easier to find Waldo on a small page or a big page? Small page. So you're increasing it. Now, that's the key thing in there is no reaction. If you're going to go to reaction, you're going to kind of feel like stuff like this. This is the hardest one people struggle with, okay, is the number of particles. Now, this makes sense. The more particles, the more entropy, correct? You have more people in this room, there's more disorder, isn't there? And I'll show you why people have more trouble with it. Now, these rules kind of go in order, okay? Like number one is the first one you look at, okay? You look at the phase, you look at the phases. And then you decrease. So when we're talking about increasing and decreasing the number of particles, we are talking about we're counting the coefficients, okay, on the reactants, the products. So if I have, so in this one right here, all right, okay. So let's look at this first example on the board, okay? As I have on the chalkboard. This is from yesterday. I have KClO3 solid goes to KCl solid plus 3/2 O2 gas. Is entropy increasing or decreasing? Why? So there's two answers to this. The easiest answer is that you're creating a gas. Anytime you create a gas, entropy is increasing. It's also increasing the number of particles. How many particles do you have in the reactants? What's the coefficient? 1. You have 1 KClO3, don't you? How many particles do you have in the products? 5/2, 2.5. So you increase the number of particles. Let's do some more examples. Predict entropy change. Lamaya, is this going to increase or decrease entropy? Well, let's go through this. The first thing you always do is you look at the state of matter. Yeah, solid, gas, yes. So what thing is that? So is the question you're asking, is the phase staying the same? No. You're creating a gas. Do gases have more or less entropy than a? So you're increasing the entropy. Okay.
So it goes from the last state of matter.
Give me a second, okay? Give me a second. I'll show you another example like this, okay? Now, there's two ways this one increases entropy. Again, you're going from a solid to a gas, okay? But you're going from 1 molecule to 2 molecules, aren't you? So 2 ways that one works. Why? You're going from 3 to 2. You're going from 3 to 2. And is the state changing? No. So that's really our first thing we want to look at. State's not changing, so it is, this one would be a decrease. This one would be a decrease. Anybody?
So it would be an increase because it's more in gas.
There's more entropy in gas.
Just to change the state of matter, that's right.
Because it changed it to a gas.
Yes.
If it would have been, if I would have made this liquid to solid, it would have decreased. Would have decreased.
Wait, a liquid to solid is a decrease?
Liquid to solid is a decrease because solids are more ordered.
Okay.
Okay, so let's say you have two solid reactions and it forms a gaseous product. Is there more entropy in the gaseous product than the two?
Yes, 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 yes. That's a very good question. Well, but I think I have an example of that. I'm not real sure. I mean, that's why I told you kind of way to say it.
There were just two solids and a gas right there.
I'll show you what he's talking about. He's talking about a. Okay, so what Balin is talking about. Okay, what Balin is talking about. Let me change my screen. I'm done with that PowerPoint. Some of it. Okay. So I'm going to work this example out. So what Balin is talking about, okay, what Balin is talking about is say, and I don't really know what, I can't really, let me Google a reaction. What Balin is talking about, which is a very good question, okay? So he's going to have, say, it's not going to say Cu, which we know is a solid, okay, plus, go back to everything, Ag, that's a solid, produces something that's a gas. Even though there are two more particles over here, yes, the gas takes precedent first, okay? The gas takes precedent first. So in any, that makes sense to you? So in a double replacement reaction, so you could say that,
What if that reproduces a double replacement reaction and it produces a gas and a solid as well?
doesn't matter what, just it is, there's a gas produced or liquid produced, it doesn't matter as long as you have one change in state, okay?
And what if it stays the same and all the particles are the same at that time?
You look at the state of matter makes biggest difference, okay?
No, I'm saying, but it's solid. What I wouldn't.
Then if it's solids, three solids, then you look at the number of particles. If the state didn't change,
What if they're both the same as what I'm asking?
then there's no change in entropy.
Okay.
There's no change. So I balance this for real quick. I think I need
Is that?
4.
I
Yeah, that's an aqueous at the end.
can't read up to
P, 4 H's, 4 H's, 6 O's. Oh man. Oh, no, that's not balanced, right? 3, that's not balanced, right? I think I need the 6 there. No, like this. Okay, so is this one I'm mixing an aqueous solution, which is a liquid, okay? An aqueous solution is a liquid with a solid to make a liquid and a aqueous solution, okay? How would you say this entropy changes?
I'm sorry, I can't read it.
It's just aqueous plus solid yields liquid plus aqueous. Is entropy, entropy is increasing, okay? Because if you really think about it, these cancel out. The biggest thing you're looking at is you no longer have a solid, do you?
Yeah.
So you now have a liquid solution, okay? So that's the biggest, so that's the thing there, okay?
So liquid and aqueous, what's the difference between them as far as?
liquid water, like only thing can really be liquid, like water, bromine, mercury. Okay. Aqueous means something that's dissolved in water.
So I'm saying like, say in the,
There's, in the grand scheme of things, there would be no difference for the purposes of this class. Okay. That makes sense to you guys talking about entropy changes today. Okay. Now, let me find one more thing. Well, if you heat it up, I don't really. So, if you heat it up, if I would say I heat this reaction up, entropy is going to increase, wouldn't it? So, any questions about what we talked about today? The other thing I want to do today is go back to what we talked about the other day, okay? And work this problem out right here, okay? This is a mass to energy problem, okay? This is a mass to energy problem. And I had an example of this in your homework the other day, but I also wanted to work, in your notes the other day, I also want to work this one out. This is one of the first things we did. So, a mass energy problem. Our first step is we need to make sure we have a balanced chemical equation. Do we have a balanced chemical equation? There we go. Do we have a balanced chemical equation, blindies? Do we have a balanced chemical equation? General rule of thumb, if they give you a coefficient, it's balanced. It has a coefficient, doesn't it? So that you assume it's balanced, okay? Without even double checking, you assume it's balanced. So I need to convert, it's a stoichiometry problem, how much heat would be produced if 1.0 grams of hydrogen peroxide react. So it's a stoichiometry problem, okay? So I take what I know and I put it over 1.0 grams H2O2 over 1, okay?
That's a stoichiometry problem.
That's what I just said.
I'm seeing.
Yeah. Molar mass goes on the bottom. Molar mass is going to be 34 grams. Over 1 mole. And here's where the stoichiometry problem kind of changes, okay? I'll check out one more step. Moles H2O2 is going on the bottom. This is the mole ratio step right here I'm about to write, isn't it? Okay. So I have 2 moles H2O2. I got this 2. Right there's my balanced chemical equation. 2 mole H2O2. Now, what's my unknown? What am I looking for in this problem? The heat. So my top of the mole ratio just becomes my delta H, okay? So negative 190 kilojoules. That everyone see that? That's from the other day. It's a stoichiometry problem. You convert from grams to moles. And if it's already in moles, you don't really need the first step. You just multiply by. But what a common mistake is, people forget to put this number right here. This 2 is a number that changes. This comes from your mole ratio comes from your balanced chemical equation.
so it goes what you know, and then the molar mass, then the mole ratio over or under kilojoules.
Yes.
Changes.
Yes, ma'am. Mm-hmm. And then so you put in your calculator, or it's going to be right around 6, a little bit less than 6. My goodness, Balin, how long did you put in the calculator?
Well, I'm putting it in again, checking the order of operation.
190 divided by 34. Negative 190 divided.
And then divide by 2.
Oh, then divided by 2. Oh, I'm sorry, I was correct. Yes, that was incorrect on my part. So it'll be right around 2.5.
Yeah.
My bad.
That's fine, put it in.
My bad, yeah. Dumb on me. A little bit less than 3. 2.7?
Yeah.
2.7, and my units are just, and it's negative 2.7.
Why the negative?
Very good question. Why is it negative? Because my heat right here, my delta H had a negative sign in front of it. If this would not have been negative, if this would have been a rare endothermic reaction, your answer would have been positive, okay? And the other kind of thing that's kind of given away with it, why it's negative also, is because here's the key word.
Release.
Yeah, release. So for release, you kind of the key word there is going to be negative also. Okay. But two things: released and then this negative sign right here. Any questions about what we talked about today? What?
Yeah.
The answer is in kilojoules, not kilojoules per mole, because my mole's canceled, my gram's canceled.
What was the used yesterday?
Kilojoules or kilojoules per mole, either one. They're used interchangeably.
So I put kilojoules on all of my.
That's fine. They're used kilojoules or kilojoules per mole yesterday.
And always is what we use.
Oh yeah, you definitely. Yeah, it's zero. I think. Yeah, it's zero.
Zero.
Yeah.
Okay, 'cause I didn't, I skipped